Homework 17, confidence intervals for population mean, standard deviation known. Video 6, controlling the margin of error using sample size. At the end of the previous video, we looked at some scenarios where we asked what would happen to the margin of error if we raised the sample size, what would happen to the margin of error if we raised the confidence level. The answers were raising sample size decreases margin of error, raising confidence level raises margin of error. When you're trying to estimate something about a population, you really don't want to let the margin of error get out of control. For example, if I said the average age of all college students was 18 with a margin of error of 30, I'm saying that the average age of college students is between -12 and 48. That's completely meaningless. You can actually control the size of the margin of error because you can control the sample size. And remember, the relationship between the two that we saw in the previous video was as the sample size goes up, the margin of error goes down. So it stands to reason that if we increase the sample size large enough, we can control how large the margin of error will get. For example, suppose we're building some confidence interval where the sample mean is 125, the population standard deviation is 20, and the confidence level is 90%. What's the smallest sample size that will keep the margin of error under 3? There's a formula for doing that, but I want to kind of show you the genesis of that formula by reminding ourselves where the margin of error comes from. I want to remind you that in the book, the author uses a lowercase m for margin of error. I will use ME. Our margin of error comes from multiplying the critical value z, which is also listed as z sub alpha divided by 2, meaning the area that has half of the remaining area, the z that has half of the remaining area to the right of it, times our standard error, which was sigma sub x bar. But our sigma sub x bar was calculated by sigma divided by the square root of n. If we know what margin of error we want, and we have the critical value because it comes from the confidence level, and we know the standard deviation, it stands to reason that we should be able to solve for n. Let's go ahead and solve for n first, and then we'll use that to answer that question. Okay, so if I wanted to solve this equation for n, the first thing I would do is probably multiply both sides by the square root of n. I would do that for 2 reasons. Number one, the thing I'm solving for is currently in a denominator and I don't want it there. Number 2, by multiplying both sides by the square root of n, it cancels the fraction. So we have the square root of n times the margin of error equals the critical value that has half of the remaining area to the right of it. Remember, the alpha represents the unshaded area, so if 90% is in the middle, then there's 10% unshaded, so half of 10% is 5%, times sigma. Okay, well, algebraically, I can get the n a little bit more by itself if I divide both sides by the margin of error. That would cancel here, and we would get the square root of n equals z with half the alpha to the right of it times sigma over the margin of error. And then from an algebraic perspective, this is alpha over 2. It's getting a little sloppy there. From an algebraic perspective, to finish solving for n, I would just have to square both sides. Now, you're not going to be asked to replicate these algebraic moves. I'm just justifying the formula I'm about to write. To get the desired sample size, we have to multiply the critical value that has half of the remaining area to the right of it times the standard deviation divided by the margin of error, and after we get the answer to that, we square the whole thing. Now this will rarely come out to be a whole number. We'll talk about what to do in terms of rounding in a minute. So we're going to use this formula on that problem. Now, the one thing we weren't given was the z, the critical value, of which the 2 critical values cut off 90% in the middle. But from the previous problem, from the previous example, 90% confidence level implies that z was 1.65. The double line arrow is a symbol for the word implies. Let me draw it a little bit more cleanly. That looks better. But a 90% confidence level, and I'm going to put CL below it just to remind you that that's the confidence level, implies Z equals 1.65. We cut off 90% in the middle, that left 5% in each tail, and then we use the Z table backwards to find them. In fact, you can take that to the bank. Anytime the confidence level is 90%, the Z is 1.65. 2 examples ago, when the confidence level was 95%, the Z is and always will be 1.96. If you do enough of these, you start remembering Z's. So, to get the desired sample size, we just got to work out this problem. A fraction that's squared. On the top is the product of the critical value, 1.65, times the standard deviation, which was 20. And downstairs, we want to divide by the margin of error that we're trying to obtain. Now, most of the time, the thing on the inside is a repeating decimal, because dividing usually comes out pretty ugly. I believe this one's gonna not be a repeating decimal. But let me tell you what I would do. I would multiply, divide, press equals, and then square. So 1.65 times 20 equals, divided by 3 equals, and then squared. This came out to be exactly 121. I was really hoping it was a decimal. I'll change the problem so it is in just a moment. So, our desired sample size is 121. So as long as we have a sample size of 121, we'll have our correct margin of error. It could be larger because raising the sample size decreases the margin of error, but that would be the smallest one. Unfortunately, this example didn't make my point because I wanted to talk about what would happen if the n came out to be a decimal. You would think you would just round it, but that's not entirely true. So let's say in this particular example, somebody said, no, I didn't want the margin of error to be 3. I wanted it to be 1 point, I don't know. Let's make it 1.4. I just want something that won't divide cleanly so I can show you what to do. So using the same example, what if the margin of error we were trying to attain for whatever reason was 1.4? Well, we would still use the same setup. It would still be the critical value, 1.65, times the standard deviation, which is 20, divided by the margin of error, which is 1.4, and then that result would get squared. This should not come out to be a whole number. I'm really kind of surprised that the first one did. That hardly ever happens. So multiply, divide, press equals, and then square. You have to press equals because of the order of operations. This is about 555.612. Now you can't pick 555.612 people to be in a sample, so you would have to round it. And this one would normally round up. But the rule for rounding here is you always round sample size up. It does not matter how small the decimal is after the decimal point. For example, if this 6 had been a 1 and it was 555.112 instead of 0.612, I would still round up. I'll tell you why in just a second. So in this case, our sample size would be 556. And the reason you always round up is simple. When sample size goes up, margin of error goes down. This is the sample size that gives you the desired margin of error. If I were to round it down, it would put the margin of error up. You never want to make margin of error larger. You'll always accept a smaller one though. So in your homework, when it asks you what is the sample size to obtain a specific margin of error, when you get the value for the sample size, always round it up. Doesn't matter how small the decimal part is. Even if this were 555.001, you would still round up to 556 because rounding the sample size down would bump the margin of error up, and we don't want to do that. All right, that's pretty much all there is in this section. Hopefully you'll believe me when I say the calculations for the confidence interval are very straightforward. I keep saying it's 5 steps, but the truth is it's 4. I don't think you're going to have to calculate the X bar in any of your problems. So you start by taking the confidence level, and cutting off the middle area, and then use the z-table to find the z's that cut that middle area off. That gives you your critical value. And then you calculate your standard error, which it's not on the board right now, but that was sigma over the square root of n. And then you multiply those two to create your margin of error, and then just add or subtract it to your x bar. Once you do a few, you realize, hey, this is actually pretty easy. If you have any questions, you know how to get a hold of me. There will be one more series of videos before test 3. The homework for that series of videos, homework 18, is already in Connect Math if you want to go ahead and take a look at it.